Okay, well, this problem, they want us to do 6 subintervals. That's problem number 2. I didn't give you a page. That would be on, let me get them. Okay, there's the page. It's on page 3 of 3. So, they want us to run 6 subintervals between 0 and 12. They want us to use L sub 6, R sub 6, M sub 6. Well, let's not worry about the rest of the parts. Let's start with L sub 6. So, first things first, delta x is end minus beginning. So that is 12 minus 0 divided by how many subintervals you want. This tells me how to begin this problem. I'm going to cut this into 2, 4, 6, 8, 10, and 12. So what I'm going to do, I'm going to pretty much run those all the way to the function itself. Okay, I'm going to do that in a minute. Give me a sec. Okay, I drew all of these heights on all these problems so we can save some time. So, if I start with 8, says find L sub 6. We already agreed that delta x was 2. So, L sub 6 is going to be 2 times, and let's see how this works. If I'm using the left-hand approximation, right, I'm going to take on, so I'm looking just at 0, 2, 4, 6, 8, 10, and 12. When I use say left, that's f of 0 plus f of 2. Basically, on this interval, I take a 2 plus f of 4 plus f of 6 plus f of 8 plus on the very last interval, I take f of 10. You should count those 1, 2, 3, 4, 5, and 6. So that is twice. And how is this going to work? Well, f of 0, it looks like, what do you think that is? To me, that looks like a 9. 8.9, I'll let it slide, not a problem. What's f of 2? F of 2, what do you think that is? To me, again, this is my vision, I'm a bit older, so I don't see as well. You see better, we're not going to disagree, as long as you're somewhat close. Alright? So I'm going to say that's 8.8. F of 4 at 4, that's a bit more than half. I'm going to say 8.2 or 8.3. It doesn't matter. F of 6, that looks like a 7 point sum. 7.3. How about f of 8? At 8, what do you think that is? That's a bit short of 6. I'm going to say 5.9. And if I take f of 10, it turns out to be a 4. So I'm going to take those, and I'm going to plug this in my calculator, and I did, and that turns out to be 86.4. They're asking, is this an underestimate or an overestimate? Think of what you're doing. You're really taking this to be the height, this to be the height, this to be the height, right? You're taking the left point of every rectangle, and the area you're given, that's really this times 2, which is 6. You're given all of that as an area. Now, would you agree that you're adding a little bit every time? So I'm going to say this is an overestimate. Alright? Now, do R sub 6. R sub 6 is right there. I'm going to go for R sub 6. Well, delta x I already found. When I look at the first interval, do you see I'm going to take the height to be the right endpoint? But I already evaluated that. But I'm going to write that down, f of 2. You should do as well as the homework. On the next interval, I'm going to take the right endpoint, the right endpoint, the right, the right, and the right. F of 6, f of 8, and f of 10. Again, when you're done, 1, 2, 3, 4, 5. We're missing one, see? That's why it's important to add f of 12. So that is 2, but you'll notice this is right there. That's 8.8. We already did that. F of 4 is right there. 8.3. F of 7.3. F of 8 is 5.9. And f of 10, we got it to be f4. The only value we don't know, we didn't evaluate f of 12 on the last problem, and that turns out to be a 1. That turns out to be 70.6. And the same deal, they're asking, is this an overestimate, an underestimate? What do you think? Well, let's see. If I glance at this, I notice I'm taking the right endpoint to be the height. The right endpoint. So it's not always the right endpoint is an under and the left point is an overestimate. It depends whether the function is growing or decaying. And in this case, do you see I'm leaving out all of these areas? So I'll say that that is an underestimate. And they want us to do a midpoint approximation, m sub 6. That's going to be 2 times. And here, when I look at the first interval, I'm going to take the midpoint to be the height, if you remember how that works. So that's f of 1. Plus, when I look at the second interval, I'm going to take the midpoint to be the height. F of 3 plus f of 5 plus f of 7 plus f of 9 plus f of 11. When you're done, 1, 2, 3, 4, 5, and 6. So here I'm going to take this to be the height. So here, unlike the left and the right, there's no overlap. I have to evaluate all of these every time. Right? Because the left and the right happen to have some in common. Actually, the majority of them are in common. So this first height, that to me looks like an 8.9. F of 3, that right there looks like an 8.5. F of 5, that right there looks like a 7.8. F of 7, that right there, it looks like a 6.8. F of, this is exactly a 5. And this is about, it looks like 2.8. And if I plug this in my calculator, that's 79.6. And I'm going to say this is the best estimate. So you have two options. You could find the right hand, the left hand, and average them. Or you could use the midpoint. It always, well, not always, I should never say always. It turns out to be a lot more accurate than the rest. Now, if I summarize everything that I did, every time I was running from A to B, most of these problems you started at 0, but that doesn't always have to be the case. Delta x is always end minus beginning divided by n. The x's are always the starting point. If you start at 0, then you really don't worry much about this. Plus I times delta x. So if I wanted the fourth interval, that's 0 in this case, plus I, which is 4 times delta x, and that gives you the first 1, 2, 3, and 4. That's the 8. The right-hand approximation, if I was to call this x sub 0 and this x sub n, and if I was to call this x sub 1, I'm just summarizing what we're doing. X sub 2, x sub 3, all the way down. The right-hand approximation seems to take delta x, and it seems the right-hand approximation takes x sub 1 to be the right endpoint, and the second x sub 2, and in the last, this is x sub n minus 1. It seems to take f of x sub n minus 1 and f of x sub n. The left-hand approximation, on the other hand, takes delta x. On the very first interval, it takes f of x sub 0. Plus, on the second interval, it takes f of x sub 1. So it seems it finds all of them except on the last interval, it takes f of x sub n minus 1. The midpoint, excuse me, takes delta x into f of x sub 1 bar plus f of x sub 2 bar plus, so on each interval, I'll tell you what that is, x sub n bar. On each interval it takes the midpoint, so x sub I bar, take the previous plus the next and divide it by 2. So to find the midpoint, take 0 plus 2 divided by 2, that's the 1. Take 2 plus 4 divided by 2, that's the 3. And that's how you find those. This is kind of summing what we're doing, right? And if I really look at the area, I'll say that's roughly the right-hand approximation, or the left-hand approximation, or the midpoint approximation. There are 3 of them. If I picked specifically the right, I'm going to say area is roughly delta x times f of x sub 1 plus f of x sub 2 plus f of x sub 3 plus f of x sub n. And if I really think about that just for a bit, I'll say that's the sum I equal 1 to n of f of x sub I delta x. And this is area roughly equal that. Now, and it turns out something I didn't discuss, I was going to discuss what happened when you double the intervals. So when I was looking at this, for example, if I was to say instead of n equal 4, what if I made them n equal 8? Wouldn't it cut those in half? And if you use the right-hand approximation, that's the area you will find, and this is what you would see. Oh wait, this was the left. I messed up big time. The left would be right there. On this interval it will be this, this. So doubling the intervals, and you'll notice instead of losing all of that red spot, you're losing less, because now you're adding this one, it wasn't there, you're adding this one, it wasn't there, and you're adding this one, it wasn't there. And if you go by the left-hand approximation, and if you cut this in half, you'll notice if I go by the right, do you see that I'm not including this area? Here, if I go by the right, do you see I'll give those rectangles, leaving this out? And here, I'm leaving this out, so it's a better approximation. The bigger n is, the better off you are. And let me show you really quick. And if you glance at those, this is n equal 10. You notice you're adding all of these areas right there. When you go to n equal 30, look, you're adding a lot less. And when you run to n equal 50, now you're adding even less. And if you were to do this is using the right, if you use the left, do you see the area you're leaving out? That's an underestimate. When you go to n equal 30, look, that area that you're leaving out is a lot less now. So this is more accurate. And when you get to the last part, do you notice that you're barely leaving anything? So the bigger n is, the better your approximation is. And therefore, to get the area to equal, not to be approximate, you take the limit as n approaches infinity of this series. And that will give you the exact area. There's a small catch, we'll talk about it next class meeting. There's the homework, only 1, 3, and 5.